Hi everybody, I'm going to go over the oxidation of alcohols and aldehydes in this video. So the main reagents that we're going to be using here are chromic acid or pyridinium chlorochromate. Okay, so they're both drawn up. For chromic acid, it comes in a variety of different flavors, but it's all the same thing essentially at the end of the day. So you might see H2CrO4, CrO3, Na2CrO7, Jones reagent, which is kind of the name that somebody gave it. But they are all functioning the same way. They're all acidic. They all have H3O+. Oftentimes you've got additions of sulfuric acid or something in there. So they all have water. They're all acidic for the chromic acid ones. The pyridinium chlorochromate, it's pretty much one thing. It will show up as PCC. That's what you'll see it as. It is neutral, does not have water or acid present. That's the point of the pyridine, is essentially this is acting as a base to scoop up anything that is acidic. So you see that this is negative, this is positive. We just have an acid base. It's essentially just a salt here, right? So the pyridinium chlorochromate, we're going to see it have different reactivity from chromic acid because of the fact that it does not have water or acid present. So let's first look at the reactivity of these and like what kinds of things you can make out of them. And then we'll talk about the mechanism afterwards. So if you have a primary alcohol and you throw chromic acid at it, you are going to get out a carboxylic acid. So you're going to see an oxidation. So we're increasing those carbon-oxygen bonds all the way as far as we absolutely can. So you're going to get a carboxylic acid. Okay, so we're trading essentially 2 CH bonds for 2 CO bonds. So if we have PCC, we're only going to get to the aldehyde. So we're going to take 2 of these and we're going to keep 1. So we're changing 1 CH bond for 1 CO bond. Okay, and if we have a secondary alcohol, that means that we've got 1 CH bond here. We're going to get to a ketone. And it doesn't matter which one you use, we're only going to get a ketone out of it. Okay. So the mechanism here is really going to tell us why exactly we have this difference in reactivity. All right, so let's check out the mechanism. So the mechanism is going to be the same for chromic acid and PCC. There's just one part in the middle where it goes one way or the other way. Okay, so at the end of the day, though, we're going to have some sort of chromium center, and we have our alcohol. Oops. And I'm just going to put an R group over here to make it general, and so that I don't have to draw that cyclohexane the whole time. Okay, so our chromium, think about how many oxygens are on it and like double bonds to oxygen. So that chromium is actually very electron poor. Okay, so our chromium in this case is going to be our electrophile, and our alcohol is going to be our nucleophile, like we've seen them used before. So we're going to go attack that chromium, and electrons are going to move up onto the oxygen. So this kind of movement is similar to what we saw in the reductions, where we attack a carbonyl and electrons move up onto the oxygen. Same thing here, right? We're going to have electrons move up onto the oxygen. Okay, so now I've got a positively charged oxygen. I've got a negatively charged oxygen. I need to do some stuff here to do a little bit of rearranging of my protons. So we're going to use this nearby OH, and you'll see why I'm using the OH here in a second. Actually, no, we'll be good. We'll use the O-. It's fine. Okay, so we'll use the O-. So we're going to deprotonate that oxygen. No, I'm not gonna. We're gonna do the cheater way. It's fine. It'll be crazy long with proton transfers if I do it that way. Okay, so we're gonna use the OH, and you'll see why. Okay, so what we've done is essentially make a good leaving group here off of the chromium. So we're gonna see water get kicked off. So we're gonna reform the oxygen chromium double bond, kick off the water there. And now I have this intermediate, okay? And I've got water, which in this, if I'm using chromic acid, I already had water, but you know what I mean. Okay, so I've got my water and I've got the two H bonds there, okay? So the water is going to act as a base. We're gonna grab one of those protons and we're going to give those CH electrons to a new CO bond, okay? And in doing so, we're going to give electrons to the chromium. All right, so we've made an aldehyde. So at this point, if I was using PCC, this is where I would stop. And the reason for that is that when we have water and acid around, when I've got an aldehyde, what can happen is if I've got that acid, then I can protonate my aldehyde. And when I've protonated my aldehyde, now it's even more susceptible to nucleophilic attack. And I have a nucleophile right there. So if I add water, and like I said, remember we've made water in the reaction, but we also have an abundance of water from the chromic acid itself. So I have no shortage of water here. So then I can get to this. And if I do a final acid-base reaction, then I have something that looks like it's just two alcohols, okay? So if I've just got two alcohols, then my chromic acid isn't going to be able to tell the difference between one alcohol and the other alcohol. So once I make this functional group, and this is called a hydrate, this is something that aldehydes particularly are susceptible of turning into. So think about the tautomerization. This is kind of the same thing where we've got an equilibrium going on between the hydrate and the aldehyde form. But when you have an aldehyde, it actually prefers the hydrate form, okay? So ketones, not so much. Ketones don't want to be in the hydrate form, but aldehydes are okay being in the hydrate form. So as soon as we make that aldehyde, if we have acid and water around, it's going to prefer that hydrate form. So it's going to keep on doing that oxidation process. But if you use PCC, it's going to stop at that aldehyde because it doesn't have acid around, okay? Oops. and it has much less water. Okay, so that's why we can get selectivity with that with PCC where we don't see it with the chromic acid. Okay, because we can see, let's just keep on going. I'm not going to go through the whole thing in class, but I can do it here. Why not? So if we just have more chromic acid, then we can just do the whole thing all over again. Okay, we can do our proton transfer here. We can again kick off that water leaving group that we just made. We still have another H there. So we can have our water come in, grab the H, make a new pyrron, give electrons to the chromium. So now the chromium has been reduced, it has gained electrons, and we have made a carboxylic acid. Okay, so the key things here in this mechanism, I know it's kind of a lot, but this is one that we want to be familiar with. The key points here is that you have to have a CH bond to make a CO bond. Okay, so no CH bonds, no oxidation, because that whole part, so this section right there is the only way that we're getting carbon oxygen pi bonds. So if you don't have a CH, so in the case of something like this, right, if we don't have an H there, we're not going anywhere with oxidation. Okay, so we're going to be trading CH bonds to one CO bond, okay, in equal amounts. So no CH, no oxidation. Okay, so that's really kind of the key things that we want to keep in mind here. Know when to use chromic acid, know when to use PCC, depending on what you want out of it. Alrighty, so I hope this was helpful, and I will see you all later, and have a good one.